Okay, so let's continue with our ray diagram discussion. Now, the side in the PowerPoint, you can see that these are the rays that we commonly use. The parallel one goes through F and so on. Intersection of these three rays gives the position of the image of that point on the object. To get a full image, we can do the same with other points. Means we only try to locate where the image going to be. We don't draw the whole thing using ray diagrams. Like so what it says is, oops, a straight line. So here's the object. So we only look for one specific point of the object. Usually, mostly, it's the tip of the object. So let's say it goes like this and makes an image over here, something like this. So we only create that starting point, the tip over here. But if we think about another ray going from here, it's going to be a messy diagram. Oops, maybe do it. So the tip appears, let's say this is F. And when that goes through F, reflects horizontally. So the image appears over here. Now this is not to the scale. I didn't measure anything. I'm just showing you a diagram, right? Now if you take another point like this over here, you can say, all right, let's take a different color. Here's another parallel light, again reflects through F, and here's one goes through F, reflects parallel. That's not right. Okay. So where they meet is this point. So likewise, we can recreate the whole image, but we don't have to. All we need to know is where one point, typically the top of the image appears, and then we just draw the rest. Okay, that is how these ray diagrams work. Okay, so now you have an idea how to draw ray diagrams for concave and convex mirrors. What's next? I've been telling you about this equation, the mirror equation, spherical mirror equation. This, once you understand where these images are forming, once you have a general idea how to draw the ray diagram, even you don't have to draw it according to the scale. Once you learn this, you can have a general idea where if the object is here, the image has to be over here, something like that. And then we can use this equation to figure out exact details. So what is the equation saying? It says 1 over dO plus 1 over di equals 1 over f. 1 over object distance plus 1 over image distance equals to 1 over focal length. It's a very convenient equation. Let's try an example. Let's try an example first. Let's say we have an object where DO is 10 centimeters. We have a concave. We're working on concave mirrors, so concave mirror with F equals let's say 4 centimeters. We want to find where the image is. Now, First of all, let's try the diagram. Now this is why the diagrams are important. You can always verify whether you're doing this right. F is 4 centimeters, so 8 centimeters or 10 centimeters. Object is somewhere over here. Let's see what happens. Comes in, goes through F. Once that comes through F, goes like this, so it's going to make an image like this. Now this is your DO, this is our DI. Graphically, if you draw this according to the scale, you can calculate this. Now let's see, without any of these, how to use the equation. 1/10. Now as long as everything's in centimeters, we don't have to convert them into meters. But if you have something like DO is 5 meters and F is 10 centimeters, either you have to convert everything to meters or to centimeters, right? Okay, 1/this plus 1/di equals 1/4. Alright, we need to find this, so 1/di plus 1/4 minus 1/10. Need to have a common denominator, so either you can do this as 0.25 minus 0.1, 1/di. So 1/di equals 0.15. What is di? Di will be 1/0.15. So we take the calculator. 1/0.15. I have 6.66 centimeters. This distance, I mean, it looks right. This is 4 centimeters over here. This is 8 centimeters over here. Yep, it kind of looks close. 6.66 centimeters. Over here, you can do it using a common denominator. 1/di equals, if you make it all 20, 4 times 5 minus 2, so 3/20. So therefore di 20/3, 6.66 centimeters. So if you use mirror equation, you can get the exact answers, but you will always need to know how to draw the diagram, because you just have the answer, but if you don't know where the light going, it's half the knowledge. All right, so let's work on few more examples. Okay, shouldn't have kept that diagram anyways. Right, F equals 4 centimeters, DO equals 10 cm concave. So we found out that the diagram looks like this. The image appeared over here, right? The image was here, the object. Magnification. Now we found that di to be 6.66 centimeters. Magnification is defined as image height over object height. It is also through this mirror equation we can define the magnification in another way, that is negative di over do. There's a negative sign comes in the front. Negative sign tells you it's inverted. There is a little bit more to this. It's called the sign convention. Let's talk about it. But here is another equation. So both of these work. The advantage here is, even if you don't know how tall this image is, you can still find the magnification just dividing these distances. It has the same ratio as the heights, right? So you can just say m equals negative di over do. So in this example, magnification is negative 6.66 over 10, that is negative 0.66. Magnification doesn't have a unit, it's just a ratio. It says negative 0.66. Negative means it's inverted. This 0.66 is less than 1, right? If this answer is less than 1, that means this thing, let me erase this. The image gonna be smaller, so it's 0.6 times smaller than the object, something like this. Okay, so when it comes to this equation, one more time, 1 over du plus 1 over di equals 1 over f. There is something called the sign convention. S-I-O-N, T-I-O-N, sign convention, T-I-O-N, I don't know, you guys check. Sign convention. What is sign convention? Let me pull up that slide. It should be somewhere in this. But it says that, okay, what it says. In this diagram, any kind of mirror, if an object or an image or the focal point, focus, appears in front of the mirror, this is the reflective side, the front side. If it is in the front, if in the front side, these numbers, these measurements are positive. The positive measurements are all positive. Like you measure this distance 10 centimeters, that's a positive value. You measure this distance 6.6, that's a positive value because it is in the front of the mirror. This focal length also, that 4 centimeters, it's in front of it, that's a positive value. So a concave mirror has a positive focal length. Now imagine again concave, you bring this object real close. Now you know that image gonna appear over here. This di is a negative number because it's in the back of the mirror. Anything that measured behind the mirror is a negative number, right? So this image distance is negative. So that is one thing. If the measurement is in the front side, it's positive. If in the back side of the mirror, it's negative. Concave mirror. Now this is kind of different when it comes to lenses, right? We're still talking about mirrors. Concave mirrors is a positive F. So that means this thing, convex, object over here, F is over here, right? Inside. So convex mirror is negative F and negative focal length. Let's move on to the next slide. So this is that magnification. Let me see where that sign convention is. Alright, here we go. If the object, image or focal point is on the reflective side, that's the front side of the mirror, its distance is positive, negative otherwise. Magnification is positive if image is upright. So magnification comes with a negative number if it is upside down, comes with a positive number if it is upright. Alright, so you have this. Now let's go back and try a couple of examples and see how this sign convention applies. Okay. Alright, you guys should work on this before me. Diamond ring 1.5, diamond place 20 centimeters from a concave mirror, the radius of curvature. Okay. So let's write down the information. HO 1.5. DO 20 cm. Radius of curvature C is 30 cm. That means F is 15 cm. It says it's a concave mirror, so F is a positive number. Determine the position of the image, its size. Alright, so you can just draw a hand sketch of this without the scale. F is 15, F is over here. Nope, it's too far. Come on, undo. F is what, 15? And DO is 20, so over here. So it's outside the focal length, so this should create a real image. Alright, let's see. If it is inside, it creates virtual images, and it's going to be upside down, so it's something like this. It looks like it's creating a large inverted image. Alright, let's do the math and find out. (20 plus 1 over di plus 15, so 1 over di, 15 minus 1 over 20. Common denominator 2 looks like 60. I think this is right. So di is 60 over 1, which is 60 centimeters. So yeah, it looks like it's going to be over here. So this di is 60 centimeters. Now, unless you draw this according to a good scale, you won't see the diagram won't look right, but you can approximately you can see it is far. Okay, so it's going to be 60 centimeters. Now let's see position of the image. So you can say it's 60 centimeters in front of the mirror, or di is positive 60 centimeters. Its size, so how big it is. Let's do this. Magnification is, so let's find what the magnification is. Right? We know that it's hi over ho. We don't know the magnification, so we have to start here. Negative di over do. Negative 60 over positive 20. Negative 60 over 20 is negative 3. So magnification is negative 3. What does this mean? Negative inverted. 3 bigger than 1 means it's 3 times bigger. So this image, yes, we have it inverted, and it's 3 times bigger. So what is our hi? hi is m times ho, 3 times 1.5, 4.5 centimeters. This should be 4.5 centimeters tall. Okay, right. Yep, think about this conceptual example. Let me see what next. You guys can work this. Diagram is there, everything's there. I will give you a new problem. I'm going to give you a new problem. So let's say f is, we have a concave, again let's say concave, 5 centimeters, do, object is 15 centimeters from it, and ho, let's say 2 cm. So find where the image is, di, find the magnification, find hi, all that. We're not going to draw the diagram this time. We'll first try the equation and then we'll go to the spray diagram. Okay, all right. So you have a concave mirror and there's an object in front of it asking where the image. By looking at these numbers, you can make a good guess. It's going to be a real upside down image. Bigger or small, we don't know. We'll figure it out. I think it's small. So one over f, 1 over 15 plus 1 over di equals 1 over 5. 1 over di equals 1 over 5 minus 1 over 15, 15, 3 minus 1, 2 over 15, di, positive 7.5 centimeters. It's positive. Alright, let's find the magnification. Negative di over do, negative 7.5 over 15, negative 0.5. Okay, small image, inverted. 0.5 less than 1, so it's a small image, negative, inverted. So how do we draw this? It's going to look like this. Now if you draw this according to the scale, you get the same thing. F, C, object is over here, in, like this. Here, if this is 2 centimeters tall, this gonna be 1 centimeters. Magnification is half plus it's inverted. Alright, let's try another one. Okay, this time let's say we have the same length, the same mirror, f equals 5 centimeters. It creates an image with di negative 8 centimeters. question is, where's the object? What's the magnification? -8 centimeters, it's inside. So that is, we are talking about those virtual images, right? It's most probably the object will be within the focal length, but let's use the equation and try. 1 over dO plus 1 over di equals 1 over f. We don't know dO. 1 over -8 equals 1 over 5. 1 over dO equals 1 over 5 plus 1 over 8. Okay, sorry about the delay. I think I clicked something to post this accidentally. Alright, so we are here. This 1 over -8 became positive when you took it to the other side. So now we have common denominator looks like 40. So 5 times 8. 8 times 5. So we have 13 over 40. So come up here. dO equals 40 over 13, which is 3.07 centimeters. And yes, it is inside the focal, right? Focus is 5. Here's the object. What's the magnification? Negative di over dO. This negative sign is for a reason. Now you see that negative and -8 cancels out over 3.07. We have 8 over 3.07 divided by 7, which is 2.6. Magnification is positive 2.6. This means upright. Positive means upright, and this means it's bigger, right? So how do we draw the image? What do we have here? F is 5, object is inside. It's going to make an image. 8 centimeters negative means behind, right? This di negative means it's behind. It's going to be over here. It's upright and it's 2.6 times bigger. So if the image is, let's say, 1 cm, this is going to be 2.6 cm. So here's the image, and you can, draw the diagram, something like this. Extend this to the center, goes like this, extend that, and complete the diagram. Okay, so without going into a further example, let me so this is something you're gonna continue. Concave mirrors, ray diagrams. I discussed this in the previous video. Sign convention one more time. Here's something to try. Okay, that's next video. One thing to remember when it comes to these things, convex mirrors, F is inside, so your F is a negative number, right? The focal length going to be negative for convex mirrors. Okay, I'm going to stop right here. Thanks everyone.